Welcome to example 1, where we're going to write the following product as a sum or difference. So when I look at the problem 5 sine of 3 theta times sine of 4 theta, I think to myself, this is a product. So I have to look at kind of the form that it's in. So I kind of say to myself, this is a product, and the product is of the form sine times sine. So the sum to product rule, or product to sum rule that I want to use, is 1/2 the cosine of u minus v minus the cosine u plus v. So in our example, angle u would represent 3 theta, and our angle v would represent 4 theta. And then I plug that all into the formula. Now we still have the 5 there, it doesn't go away. So I 5 times 1/2 the cosine of 3 theta minus 4 theta minus cosine of 3 theta plus 4 theta. Next, I am going to take the 5 times the 1/2 to get 5 halves. 3 theta minus 4 theta becomes a negative theta. 3 theta plus 4 theta becomes 7 theta. And when you use your odd and even properties, the cosine of negative theta is cosine of positive theta. So I have turned the original product into the sum or difference of 5 halves the cosine theta minus cosine 7 theta. And here we are at example 2, where now we're going to take something that is a sum or difference and write it as a product. So we're going to change the operation from addition and subtraction to multiplication. So when I'm looking at this, I'm thinking to myself, this is a sum of the form cosine of an angle plus a cosine of an angle. So the formula that I'm going to utilize is going to be the cosine u plus cosine v equals 2 cosine u plus v divided by 2 times, that's the product, cosine of u minus v over 2. So I figured that out by looking at the form, that it was a cosine of something plus cosine of something. Now don't let this problem throw you off. U in this case is a binomial. The angle is theta plus 2 pi. Then v is theta. So then I'm going to take those two angles and I'm going to plug them into the formula, which yields 2 times the cosine of theta plus 2 theta plus theta all over 2, cosine of theta plus 2 pi minus theta all over 2. The remaining parts of this is just simplification. In the first cosine, I can combine the thetas, so I get 2 cosine 2 theta plus 2 pi divided by 2. And then in the second angle of cosine, the thetas cancel, leaving me with 2 pi over 2. In the next step, I can factor out a 2 out of the numerator of the first angle, and I can reduce 2 pi over 2 to pi. Next, I can evaluate the cosine of pi is -1. The 2's cancel, so I'm left with theta plus pi. So my final answer when I take the -1 times the 2 is -2 cosine of theta plus pi. So I have turned something that was the sum of 2 cosines into a product, or in this case, the product of -2 times the cosine of theta plus pi. And welcome to example 3, where we're going to use the sum to product formulas to find the exact values of the expression. So when I see the cosine of 165 minus the cosine of 75, those are not angles that I can find the exact values of on the unit circle. Now certainly you could break those down using the sum and difference formulas. There's more than one way that you could probably go about this, but what I notice is that it's a difference of the form cosine of an angle minus cosine of an angle. So I can convert this to a product using the formula -2 sine u plus v divided by 2 times the sine of u minus v over 2, where I'm going to use u is 165 and v is 75 degrees. So using that information and plugging it into the formula, okay, I have -2 sine of 165 plus 75 divided by 2, sine of 165 minus 75 over 2. Next, I do some arithmetic. 165 plus 75 is 240. 165 minus 75 is 90. When I divide each of those angles by 2, then I get negative 2 times the sine of 120 times the sine of 45. And then I can evaluate the sine of 120 and the sine of 45. The sine of 120 is a second quadrant angle. Sine is positive in the second quadrant, so it's root 3 over 2. The sine of 45 is root 2 over 2. And when I multiply the numerators together, I get negative 2 times root 6. When I multiply the denominators together to get 4, and I can reduce 2 over 4 for my final answer of negative root 6 over 2. And welcome to example 4. We're going to find the solutions of the equation in the interval from 0 to 2 pi. And I'm going to leave it to you to use a graphing calculator to verify your answers just in the sake of time for this video. I see that I have the cosine of 2x minus the cosine of 6x. So obviously when you look at the cosine of 2x, you might go to the double angle formulas, but hopefully you might recognize that this is a difference of the form cosine minus cosine. So maybe converting it using the sum and the product sum to product formula is helpful. So we're once again going to use negative 2 sine of u plus v over 2 sine of u minus v over 2. And in this case, u is our 2x and v is our 6x. So when I apply that to the formula, I get negative 2 sine of 2x plus 6x over 2 sine of 2x minus 6x over 2. And remember, this is an equation equaling 0. So my next step is to simplify those angles. 2x plus 6x gives me 8x. 2x minus 6x gives me negative 4x. In the next step, I can simplify 8x over 2 to be 4x. And I can simplify negative 4x over 2 to be negative 2x. Now, to make my life a little bit easier, we can use the even and odd identities to remind ourselves that the sign of negative 2x, the negative can come on the outside. And when I combine it with the negative 2, then the 2 would become positive. So I'm left with 2 sine 4x sine 2x equals 0. And I can divide both sides by 2 to get rid of that factor of 2. And why is this helpful? Why do we want to convert this from a sum to a product? Because now that I've got the sine 4x times the sine of 2x equals 0, I can use the zero product property. So I can set each of those functions equal to 0. All right, so here's what's going on. We have multiple angles. So when I need to solve the sine of 4x is equal to 0, I can use u substitution where u is equal to 4x. So the sine of u is equal to 0. And y coordinates are 0 at 0 and pi. But I still need to do the general case because when you do the sine of 4x, you're really taking 4 sine curves and putting it in the size of one sine curve. So that means we're going to get more than just 2 angles in one revolution. So you will notice in the next steps that I took 4x is equal to 0 plus 2 pi n, and 4x is equal to pi plus 2 pi n, and divided them all by 4, yielding me with x is equal to 0 plus pi over 2n, and x plus pi over 4 plus pi over 2n. I used a chart to hopefully exemplify why we have so many solutions in this problem. Okay, the reason we have so many, and just ignore the blue for right now, the reason we have so many solutions in this problem is when n is 0, x is 0 degrees. But when n is 1, I get pi over 2. That is still in between 0 and 2 pi. When n is 2, that's 0 plus pi, yielding me pi. When I take 0 plus pi over 2 times 3, it's 3 pi over 2. And when I take 4 times pi over 2, I get 2 pi. So in this case, 2 pi, since it's not included in the interval, this would not be part of a solution. And I don't have to go any farther in my chart. Now when I look at x equals pi over 4 plus pi over 2n, again, when n is 0, I get a solution of pi over 4. When n is 1, that's pi over 4 plus pi over 2. And when I get a common denominator of 2 pi over 4, I get 3 pi over 4. When n is 2, that's pi over 4 plus pi over 2 times 2, which is pi. And when I get a common denominator, that yields 5 pi over 4. When n is 3, that's pi over 4 plus 3 pi over 2. Again, when I get a common denominator, I get 7 pi over 4. Once n is equal to 4, I would yield something that exceeds 2 pi. So far, my answers are 0, pi over 2, pi, 3 pi over 2, pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. And what I still haven't done is I still haven't taken this second factor, which is the sine of 2x, and solved for it. Now, there's two ways that you could go about solving for the sine of 2x is equal to 0. I could do it by u substitution. So u equals 2x, the sine of u is equal to 0. So that means u can be 0 or pi plus 2 pi over n. When I take 0 plus 2 over pi n and divide it by 2 to isolate the x, I get 0 and pi, and then the next iteration would be 2 pi, which exceeds 2 pi. When I let 2x equals pi plus 2 pi over n, I get x is equal to pi over 2 plus pi, and when I divide by 2, yielding pi over 2, but then when n equals 1, I get 3 pi over 2. So 0, pi, pi over 2, and 3 pi over 2 are also solutions, and we did get those already from the previous problem, but we still need to cover that. Another way that I could have solved sine of 2x equals 0 is by using the double angle formula of 2 sine x cosine x equals 0. I can set sine x equal to 0, cosine x equal to 0, and notice how I still get the same answers of 0, pi, pi over 2, and 3 pi over 2 when I do it that way. And welcome to example 5, where we're going to verify the identity algebraically. Again, I'm going to leave it to you to use a graphing utility to check your result graphically. All right, this was a little counterintuitive when I did this. I immediately wanted to start with the right-hand side because I thought there was more to do, and you can. But I want to show you how we could also work with the left side as well. When I think of the sine of 4 theta, I can think of that as the sine of 2 theta plus 2 theta. And then I can use my sum and difference rule, where sine, cosine, cosine, sine, 2 theta, 2 theta, 2 theta, 2 theta. And because it's a sum of two angles, I use a sum in the difference formula. Or excuse me, the sum formula. Well, how many of those do I have? I can use the commutative property of multiplication to rewrite cosine 2 theta, sine 2 theta as the sine of 2 theta, cosine 2 theta. And then you have like terms. I have two of the same term. So I have 2 sine 2 theta, cosine 2 theta. Well, if I kind of compare it to what I'm going to, I need a sine theta and a cosine theta. So I'm going to rewrite the sine of 2 theta, the double angle, as 2 sine theta, cosine theta. And if I look closely, the cosine of 2 theta is equal to 1 minus 2 sine squared theta, so I substitute that. And voila, 2 times 2 gives me 4 sine theta, cosine theta, times 1 minus 2 sine squared theta, and I've proven the identity. So the learning opportunity number 3 is to try page 383, numbers 63 to 81 odd, and 87 to 97 odd, and you will have the class period after this to work on it. Look forward to helping you. Have a good one.